All right. So to practice, left the theorem here at the top. Consider each vector field below. We're going to write down 4 vector fields, okay? And we will ask of all of these which are conservative. So the 4 vector fields, here they are, capital F arrow of x comma y equals bracket, angle bracket 6xy comma 3x squared plus 4y cubed. For the second one, the vector field is defined by cosine of x comma y sine of x. For the third vector field, we have f of x comma y is angle bracket xy comma x plus y squared. And for the fourth example of a vector field that we're going to see whether it's conservative or not is angle bracket y plus sine of y comma x plus x cosine of y. Okay, so let's take the first one. So in the first one, sorry, I'll just rewrite it. The first one was f of x comma y equals 6xy comma 3x squared plus 4y cubed. Now this is all new for us, so why don't we just real slow write down capital P. We'll identify that capital P in this example is 6xy. Capital Q, you probably won't write this in the future, is 3x squared plus 4y cubed. But it's new, so even this thing of identifying the pieces, like we had back here, just thought let's just do it here, right? First time after all. Okay, let's compute partial derivative of p with respect to y and partial derivative of q with respect to x. So partial p with respect to y is 6x, and the partial derivative of q with respect to x is 6x from there plus 0. Okay, these match, yeah? So because we got a 6x and a 6x, we've got this matching here, we will therefore, by the theorem, conclude so this f is conservative. Let's look at the next example. We have the vector field f of xy was cosine of x comma y sine of x. So we need to compute the partial derivative of the first component with respect to y. This with respect to y, well, there's no y's there, so the value we get is 0. Take the second component, which, this part, y sine x is our q now. So that with respect to x is going to give us y cosine of x. Okay, so f is not conservative. Let's look at the next example. So our third example of a vector field, f of x comma y, was xy comma x plus y squared. So take the first part, call that p, right, and differentiate with respect to y. Take the second part, call that q, differentiate that with respect to x. So each of the components we're differentiating with respect to not the variable you'd normally expect, but it's just because of this crossing of things that occurs with Clairaut's theorem. So partial derivative of p with respect to y is x, and partial derivative of q with respect to x is 1. So since x is not equal to 1, f is not conservative. And one more vector field here. Let's look at the last one here is y plus sine of y comma x plus x cosine of y. So we'll take the first component, differentiate with respect to y, and get 1 plus cosine of y. We'll take a look at the second component and differentiate with respect to x, and we'll get 1 plus, okay, if we differentiate x cosine y with respect to x, just get cosine y. So this is good. So here, so f is conservative. Is conservative. Okay. Now, since this first vector field here we have seen is conservative, let's do the following follow-up. So, question, since the vector field capital F equals 6xy comma 3x squared plus 4y cubed. Since this is conservative, we have a conservative vector field. Let's find a potential function. Find a potential function, lowercase f. Okay, well, this is new, but it answers the other big question that we have in mind. And here's the thing, whatever that potential function lowercase f is, we know that when you take it and you differentiate with respect to x, you need to get 6xy. When you take it and you differentiate with respect to y, we know that we have to get 3x squared plus 4y cubed. And this is really all we need. We're going to basically build what we need, right? So take this right here, and partial derivative of whatever f is with respect to x is supposed to give you 6xy. What we're really going to do actually is just integrate with respect to x. And when you do that, we'll say that the function lowercase f itself needs to be of the following form. So if we integrate, treating y like a variable, we'll have here 3x squared y plus a constant. But let's be very careful about how we write this constant. We're actually going to write here g of y. Now let me clarify why we're doing why we write g of y here. What I mean is g of y is written here to mean that we have here it's a function, but only of y. So what's going to be written where the g of y is, this represents some function, but the function can mention y, it cannot mention x. So this is really a constant with respect to x. Okay, so 3x squared plus, instead of saying a capital C, that's too cheap for us right now, 3x squared y plus anything that does not mention y. Sorry, that does not mention x. Okay, I hope we're okay with this so far, because what we're going to do now is take what's written here, this equation, we're going to differentiate with respect to y, because then we'll have f sub y of x comma y. Right, and that would equal, we'll take this, differentiate each term with respect to y. The first term, 3x squared y, will differentiate to 3x squared. The second term is g of y. Well, look, this is a normal derivative, so this will just be, let's just write g prime of y. Our prime is understood that the derivative is with respect to the variable y, because that's the only variable there. Well, then we know that f sub y is supposed to look like this. We've got f sub y looking like that. So actually what we're going to do is just bring this thingy down here and set equal. So 3x squared plus 4y cubed. Okay, then if we take a look at this equation right here, if we subtract 3x squared on both sides, we get g prime of y is equal to 4y cubed. And then what we need to do here is just integrate with respect to y and get g of y is equal to y to the fourth plus, well, now it should be just a constant. We don't want this thingy mentioning x. We've already taken care of what's going on with x over there. So now that we know what g of y is supposed to look like, we can take this alongside this and now say, aha, f of x comma y should look like 3x squared y plus, and then it said g of y here, but now we know g of y should be of the form y to the fourth plus c. Now, we're not quite done. We're so close to done. As far as an answer that works, one answer is f of x comma y is equal to 3x squared y plus y to the fourth. And another answer, so staring at this, we can get the answer that we just wrote down, or another answer is f of x comma y is equal to 3x squared y plus y to the fourth plus, well, how about 309? Okay. The point is, just like with antiderivatives, so potential function, think about potential function as being like an antiderivative. It's the antiderivative if by derivative we meant the gradient. So just like there are multiple antiderivatives in Calc 1, there are multiple potential functions. So here's it's maybe a slightly silly interactive question, but I'd like you to please give this a try. Why are both of the, so this and this, we're providing two answers apparently, so why are both potential functions? So why are both f of x comma y equal to 3x squared y plus y to the fourth, and f of x comma y equals 3x squared y plus y to the fourth plus 309? Why are these both? Why are both blah and blah potential functions of capital F equaled, it's been a while, it's up here, let's just copy paste this, oops, let's try that again, we will take this thingy here and copy paste this down here to really finish off the question. Make sure that the question is clear on its own. Okay, there's lots of ways you could take the interactive question. So you could go from the practical level and kind of rehash what's going on here. You could just actually verify that what we have are both potential functions, just based on what a potential function is defined to be. Take it whichever way you want. I just want you to think about some of the things that are going on here. And we will do another example of a thing like this in just a moment.